Hey everyone, this is the Introduction to Computing and Programming in Python, a Multimedia Approach, the fourth edition, Chapter 12. So to begin, we're going to look at the chapter objectives. So the media learning goals for this chapter are to write a program or to write programs to directly access and use text information from the internet, to translate a sound or picture to text and translate text back to a sound or picture, and to hide a message in a picture. The computer science goals for this chapter are to use a program to access the internet to show that information can be encoded in many ways. So networks. So a network is two or more computers communicating. Networks are formed when distinct computers communicate via some mechanism. Rarely does the communication take place of 0 and 1 voltages over a wire. Too hard to make work over distances. More common is the use of frequencies, maybe in the sound range or maybe not. For example, a modem, modulator, demodulator, takes your computer's zeros and ones and translates them into sound frequencies that can pass over the sound wire and be decoded on the other side. So I'm sure all of you are probably watching this video from your house right now, using your own network, right? Where you have your phone, your Roku's, your Apple TVs, your whatever, um, your computers, everything's on your home network. So I'm pretty sure that you guys are all familiar with at least the concept of what a network is. So networks are everywhere. If you're driving a newer car, you probably have a network in there. There are a lot of computers in your car controlling airflow, gas flow, making the airbags work, and they communicate. You can have a network in your own home or even on an airplane. It can use radio signals for communication. That's wireless, or string a cable between two computers, also called being hardwired. And networks have layers. Networks have several layers to them. At the bottom level is the physical substrate. What are the signals being passed on? So this is the actual the copper wire or whatever in the cable itself that passes your internet access in your from your ISP or whoever. Levels higher determine how data is encoded. Do we use sound frequencies to represent zeros and ones, or radio waves? Do we send a bit at a time, a byte at a time, or in packets larger than that? Levels even higher than that determine the protocol of communication. How do I address a particular computer I want to talk to, or many computers? How do I tell a computer that I want to talk to it, or that I'm starting to send data to it? What's it supposed to do? What's it supposed to do with it when we're done? Ethernet is a common mid-level protocol. Ethernet specifies some aspects of how data is encoded, and computers are specified. For example, each computer on an Ethernet network has a deep down inside the computer address that it identifies by, and this address is unique. But Ethernet can work over a variety of physical substrates. For example, you can run Ethernet over wireless, radio, or over coax cable, where you hear terms like 10 base T. Internet is a collection of networks. An internet is a network of networks. If you put a device in your home so that your computer can talk to one another, you have a network. A wireless base station or an Ethernet router, perhaps. You can probably reach printers on your network or copy files between computers. If you now connect your network through an ISP to the global internet, um, your home network becomes part of yet another part of the internet. Internet is based on agreements on encodings. The internet is based on a set of agreements about how computers will be addressed. A set of four numbers, each 1 byte now, soon to grow. This is IP4 to IP6. Right, sorry, IPv4 to IPv6, separated by a period. So in this example, we see an IP address of 10.1.0.5. Um, a way of associating domain names with these numbers, like www.cnn.com, which really is a name that resolves to a set of four numbers using domain name servers, or DNS. How computers will communicate. That data will be put into packets with various pieces in them. That computer will format their data and talk to one another using TCP/IP. How packets are routed around the network to find their destination. So these are the three agreements that are required for the internet to actually function. So the internet is not new. The internet agreements date back 40 years. It was originally set up for military applications. One of the features of the internet is that packets find their destination even if part of the internet is destroyed, damaged, or subject to censorship. The internet originally had only a handful of computers or nodes on it, but it has grown dramatically in recent years. And this was written in 2016, so some of this information is even more outdated than you can imagine, as you all know how popular the internet is right now. So protocols on the internet, but all that just lets us pass data back and forth. What does the data say, or what does the data do? One of the first applications placed on top of the internet was electronic mail or email. The mail protocols have evolved over time to their standard forms today. The FTP, or File Transfer Protocol, allows computers to move files between each other. It defines what one side will say to the other when copying a file over. For example, STO file name, and how the file will be encoded. And then there's the web. The web dates back to the 80s, but before there were graphical browsers like Netscape Navigator, Internet Explorer, and the first NCSA Mosaic. The web is again a set of agreements started by Tim Berners-Lee on how to refer to everything on the internet, the URL, Uniform Resource Locator, on how to create documents that refer to things over the internet, HTTP, Hypertext Transfer Protocol, or on how those documents will be formatted using HTML, Hypertext Markup Language. Hypertext, nonlinear text. Hypertext is a term invented by Ted Nelson in the 1960s. It refers to text that is nonlinear, which the computer makes possible. You're familiar with this on the web. Read a little on a page. Click. Continue reading on some other page anywhere on the internet. This is written in HTML. The point of the web is hypertext. Tim Berners-Lee wanted a way to create readable documents that could reference material anywhere on the internet in a hypertext format. There are technical flaws of what he did. For example, the phenomena of dead links couldn't happen in other hypertext systems before the web. But it worked and has become a worldwide standard. HTTP, Hypertext Transfer Protocol. HTTP defines a very simple protocol for how to exchange information between computers. It defines the pieces of communication. What resource do you want? Where is it? Okay, here's the type of thing it is, JPEG, HTML, whatever, and here it is. And the words that the computers say to one another, not complex words like uh, get, put, and OK. Uniform Resource Locator, or URL. URLs allow us to reference any material anywhere on the internet. Strictly speaking, any computer providing a protocol accessible via URL. Just putting your computer on the internet does not mean that all of your files are accessible to everyone on the internet. URLs have four parts: the protocol to use to reach the resource, the domain name of the computer where the resource is, the path on the computer to the resource, and the name of the resource. Here's an example of a URL. So this is a website, cc.gatech.edu. Not really sure where this goes to. But as you can see in the beginning, you see the protocol HTTP, which I'm sure you all seen before typing different things. We see colon // www dot, right? That's the domain name. And then slash index.html. That points to the file name. As you can see on the bottom, similarly, if we were to use FTP, say we wanted to get this SIG CSE 2003 PDF about whatever it's about, we could actually use an FTP program like FileZilla, for example, and we could actually point to the protocol FTP, the domain name like we had before. There's the path, right, locally on that server, and then there's the file name, which is what we want to actually get. Um, and then again, like we mentioned previously, there's a DNS, or domain name server, which actually will translate this www.cc.gatech.edu to something as simple as a 4 byte IP address, something like maybe 10.10.1.1. something to that effect. So what if there is no path? Web servers, or programs that understand HTTP protocol, typically have a special directory that they serve from. Files in that special directory are directly referable without specifying a path. Subdirectories within the directory can be accessed in terms of a path, but always starting from the server directory, so not everything on your computer is always accessible. A browser is a client. Your web browser is called a client accessing a web server. Programs like Internet Explorer, Firefox, Google Chrome, Safari understand a lot about Internet protocols. They know how to interpret HTML and display it graphically. If the HTML references other resources like a JPEG picture, the client fetches them and displays them where appropriate. Your client also knows the details of the HTTP and maybe FTP, Mail2, Gopher, etc. protocols so that it can request the resources you request. You don't need a browser to use the internet. Your mail program also understands some internet protocols. JES even knows a little about one of the mail protocols, SMTP, or Simple Mail Transfer Protocol, so that it can email homework to your instructor if it's set up. Python and other languages have modules that allow you to use these protocols. In Python, we can read any URL as if it was a file. So here's an example of how to open a URL and read it. So we import URL lib, right? We create a variable called connection equals URL lib.url open. We open cnn.com. We say weather equals connection.read, and then we say connection.close. So we can actually take this as an example. So let's import URL lib. Actually, I'm just going to do this in the command window on the bottom. So we're going to say import URL lib. Awesome, it imported. We're going to say, let me go back here. Connection equals URL lib.url open. So we're going to say connection equals URL lib.url open. And we're going to say HTTP cnn.com. Oops, sorry. www.cnn.com. Let this work. Awesome. Took a second, but it worked. We're gonna say weather equals connection.read. Weather equals connection.read. Awesome. And then we're gonna say, believe just connection.close. Yep. We're gonna say connection.close. So now we created something called weather. Let's see what it actually outputs. Sweet. So this actually went to CNN.com, right? It went to the website, and it grabbed what their HTML of that web page actually is. So let's see if we can do something real quick. This is actually a very massive object. I don't know. Let's see. What we're gonna do is we're gonna copy this HTML. I'm gonna go to here. We're gonna copy it. We're gonna open Notepad++. We're gonna save this as test. HTML. HTML. We're gonna put it on desktop. You can put it wherever you guys would like to. Save it. So as you can see, it formatted now as an HTML document. So now if I go to my desktop, week one assignment. If I open HTML, awesome. So actually you can see based on this, it's not perfect, but you can actually see that for the most part, if I go to CNN.com, right, we see that it looks just like CNN looks, sorry, for the most part, again, right? Not too far off, right? That's all done. We did that entirely with Python. Cool. All right, continuing, we can automating access to CSV data. For example, we can import it, URL lib again. We can write a function. We define a function called find population URL that passes an input variable called state. We create a connection where we open the URL to this location of census data. We read the lines, we close it, and then we go through each line, we split it at the comma, and then we do some other manipulation to it, and then output it. So as you can see, um, let's go through here. So accessing a CSV data from disk, you can see this is actually what the previous example would kind of look like if you actually went through it, where you can see that we're actually pulling in data, um, and then it results in some CSV that you can actually open with Excel. We're going to skip these examples. You're not actually going to have to do anything with CSVs for this class, but again, if you want to take this example, you're more than welcome to. Um, it's nice to know how to manipulate different things, how to export to a text file, different things like that. Um, what's nice if you think about it programmatically is that the CSV is honestly just like a list, right? A comma separated value. So that's comparable to what a list is, right? If we have a list, for example, if I made a list, if I said test test list equals 1, 2, 3, 4, 5, 6, 7. Technically, right, this is a CSV, right? What is the CSV? Comma separated value. These are commas. These are values. They're separated by this. So technically, right, it's the same kind of concept. So again, you can take this example if you want to go through it. Um, Based on this, I don't have the death penalty CSV locally. Um, so if I did though, and I ran through this, right, it's going to say, well, we can just go through this real quick. So it gets all the data, it does all that stuff. It sets the max to -1, right? So what this is trying to do is find the highest number of executions. So it initializes a variable called max to -1 and max country to none. And then for row in CSV, we learned this for loop previously, right? So for every row in this file, try to get the country, which is the zero index of row, and the execution, which turns out to be the 14th index in row, right? We can see this 1, 2, 3, 4, yada, yada, yada. We see executions is in the 14th, right? You can see 0 through 15 as they label it here. So executions is in the 14th index. So it says if executions is greater than max, so max is -1 right now. So if we see 0, even if they had 0 executions in this case, we update max. So as we go through here, we keep updating the max until you actually find what the max executions is, right? If it doesn't have uh, um, if it doesn't have an execution number, we get to this except, we pass, and then after it goes through every single row in the CSV, at the very end, we print out the max country and the max number. So in this case, we see that Saudi Arabia had 423 executions. So again, based on this if statement, if executions is less or is greater than max, max equals executions, max country equals country, right? So we're saying, for example, if we look at this, we're saying we go to Afghanistan. We say, is your executions number that higher than the previous executions? If the previous execution was 15, we don't update, right? That country would stay. If the previous executions was 13, we say, oh, Afghanistan has more executions than the previous country or the previous max executions number, right? We're going to update. So now our new number becomes 14 and Afghanistan, and then we continue. Does Algeria have some? No. In this case, it passes because there's no recorded executions. What about the Bahamas? No recorded, right? So we continue, and then as we go through this entire death penalty CSV, we can see that we output Saudi Arabia at 423 at the end. So storing a file is different. It is possible to send information to a web server. That's how search functions, forms, etc. work. But it's more complicated than just reading, and it requires an accepting program on the web server. It isn't hard to send information to an FTP server though. But first, let's make our temperature finding function useful by directly reading the weather page. FTP and HTTP servers. FTP allows us to move files between computers on the internet, including our computer and the computer hosting our HTTP server. Computers running HTTP servers often also run FTP servers to allow for manipulation of web files. You can do this with specialized FTP clients or with Python and Jython. So here's an example of uploading to an FTP server. So import FTP lib, we connect to it, There's the login, Guzdial, and my password. So let's see if this actually works. I haven't actually tested this, so we'll see if we can actually get something to happen. So we're going to import ftplib. Okay, imported. We're going to say connect ftplib, ftp, connect equals ftplib.ftp. And then inside here we see cleon.cc gatec.edu. Let's see if we can connect. Awesome, it didn't air out. We're going to say connect.login, connect.login. We're going to say pass two parameters, right? A username and password. Guzdial, and I believe it was my password. Just double check. Guzdial and my password. Name connect was not valid. Connect.login. Yeah, I don't think it likes it. Let's try it again. Connect equals ftp lib. That seems fine. Connect dot login. Again, these are examples that were from the book. So if they don't work, the book is outdated. Just going through what the book has. Okay, so it's not actually liking that. I don't see a valid reason why it would not like that. Let me see what connect equals. Let's try one more thing. Let's say Steven test. It's not it's not being a fan right now. Let's try one more thing. We're gonna import ftp lib. We're gonna say connect equals ftp lib.ftp. I wish I would have saved that. Copy that. I'm going to say connect.login. Again, if I didn't mention previously, the up and down arrows are what controls the going through the command window down here. All right, so we're going to load this program. It's going to ask us to save. We're going to just call it test like we normally do. We're going to replace it. That's fine. We're going to say load program. Cool. It actually loaded. So if I weird, I don't know why it's not doing that. Okay, so that we can continue with this example then. Let's actually try to print out connect and see what happens. Weird. It's not printing anything. Yeah, so I'm not really sure. I've never actually done too much with the FTP library. Again, you're not going to actually need it for this class as well, but again, the book wants to mention it because it is a protocol that the internet does rely on for moving files and various things like that. Um, so definitely be familiar with the idea of FTP, but as far as actually implementing it and using it, like in their example, it's not actually required. So the interactive web. The first use of HTTP was just to send around static pages and images and sounds and so forth. Later extensions allowed for users providing input to the server, such as doing searches. Originally, this was just a CGI, Common Gateway Interface scripts. Later, servlets and applets and PHP and various other methods developed. Interactive web requires programs to generate HTML. Typically, a web server will have some directory specified special. Files referenced there aren't just returned to the client. Instead, the files are executed and the result is returned to the input. There's even a mechanism where the client can provide input to the executed files. For example, a search string. Those special files would generate HTML. The generated HTML might be based on up the minute information like stock quotes, temperature sensors, database queries, etc. Thus, to have an interactive web, we need to write programs that write HTML. Using text to map between any media. We can map anything to text. We can map text back to anything. This allows us to do all kinds of transformations. Sounds into Excel and back again, sounds into pictures, pictures and sounds into lists, formatted text, and back again. Why care about media transformations? Transformed digital media can be more easily transmitted. For example, transfer of binary files over email is often accomplished by converting to text. We can encode additional information to check for and even correct errors in transmission. It allows us to use the media in new contexts, like storing it in databases. Some transformations of media are made easier when the media are in new formats. Mapping sound to text. Sound is very simple, or sound is simply a series of numbers, sample values. To convert them to text means to simply create a long series of numbers. We can store them to a file to manipulate them elsewhere. Copying a sound to text. So in this example, we define a function called sound to text. Notice the camel casing in the function name. It takes in two parameters, sound as the first input and file name as the second. We create a variable called file. We set it equal to the method called open. We pass open two parameters, file name, and the type of how it's going to actually read the file or open the file. Continuing, we see we have a for loop. For s in get samples, and then we have sound. File dot write, so we're writing to wherever we opened or whatever we passed in. The string get sample s plus a new line, and then we close it. So as you can see in that example, the get sample returns a long list containing just numbers. And what do we know that knows how to deal with a long list of numbers? That's Excel, right? And then we can simply open our text or txt file in Excel, and then we'll get this. So because we did the backslash n, that's the encoding for a new line. So it's going to print each number on its own line, and then close the file when it's done. So then, as you can see, that's our sound file that we have right here. Is the results from the get samples from the for loop of opening the sound file, copying a sound to text. So we can process the sound in Excel. We can graph the sound, see like below. A signal view is simply the graph of the sample values. We can add a column and do some modifications to the original sound. Fill down to get them all, and we can increase the volume that way as well. Some forms of Excel might not work. So again, we can tell even by how this pop-up looks that this pop-up is very outdated. This looks like Windows XP or something to that age. So obviously, Excel is much more powerful now. So this you probably won't see this if you decide to graph your sound file as you convert it. Reading text back into a sound. After we process the sound as text in Excel, we can save it back to a sound. First, copy the column you want into a new worksheet. Then save the worksheet as a text file. Get the full path name of the new .txt file to use in JES. Issues in reading the text back into a sound. We can't be sure how many numbers are in the file. We can't be sure that the numbers will all fit into the sound we've chosen to serve as our target. What we want to do is, as long as we're not out of numbers in the file, and as long as we still have room in the sound, copy a number out of the file and put it into the sample in the sound. Then go to the next number and the next sample. So reading the text back to sound. So as you can see in this example, we write a function called define text to sound that takes one input, which is file name. The first thing we do, as we can see by the comment, is set up the sound. What that means is we're actually going to call the make sound function that calls the get media path, and we point that to a WAV file, right? And that's assigned to our sound variable. Then we say create another variable called sound index. We assign that to the number 1. Another comment says set up the file. So we're going to actually open a file, we're going to read the lines, and we're going to close it. And then we set the file index, which is a new variable, to 0. And then the comment says keep going until run out of sound space or run out of file contents. So we have a while loop, which says while the sound index is less than the get length of sound, and the file index is less than the length of the contents. And what we do is based on the content index, right? File index, get the file name. It goes through and it sets the sample value of the sound file that we got on the above. It updates the indices right? In the sound file that we have, and then at the end it returns the sound. So in this case, we can actually read the text back from the file that we had. So as previously we had the txt file of all the sound, we can actually read that back and create a sound object out of it. So the something you might not have seen before is the while loop, right? So let's explain what this statement says. While keeps executing the block until the logical expression is false. The logical expression is made up of three things. It's made up of sound is less than get length of sound. So it says while the index is not yet at the end of the sound, so there's still room for more numbers. So that's the first part. And then there's an and. So both parts have to be true for the whole thing to be true. So if I said, for example, if you asked your parents, can I have a cookie, for example? And your dad says yes and your mom says yes, that's a yes, right? If your dad says yes and your mom says no, that's a no. If your dad says no and your mom says yes, also a no. If your both parents say no, it's a no. So that's basically how the and works, right? Both have to be true. So your mom and dad both have to say yes, you can have a cookie before you can actually have the cookie. And that's how an and operator actually works. Continuing, we say file index is less than the length of the contents. So while there are any numbers left in the file, i.e. the file index is before the length of the contents of the file. We could do pictures, but they're more complicated. Pictures aren't just a single number for each pixel. To recreate a picture in text, we need to record for each pixel the X and Y positions, and then the RGB, or red, green, and blue component values. That requires more structured text than simply a long line of numbers. Let's do that in just a few minutes. So mapping from text to anything. Once we've converted to text or numbers, we can do anything we want, like mapping from sound to pictures. How do we simply decide on a representation? How do we map sample values to colors? So in this example, um, we have sound to picture. So we say picture equals get media path, and we pass in a JPEG. Sound index equals 0. We say 4p in get pixels, which we've done before, right? We're going to get all the pixels from the picture. We say if the sound index equals the get length of the sound, break. And break actually means to exit out of the statement. I think we will talk about that in a second. Sample equals get the sample value at the sound. So we pass in two parameters, the sound itself and then the sound index. If the sample is greater than 1,000, set it to red. If it's less than negative 1,000, set it to blue. And if it's between either of those numbers, set it to green. And then we increase the sound index and continue. And at the very end, after the for loop's done, after the for loop's exited, we return the picture. So what they're doing in this example is everything that's greater than 1,000 is red, less than 1,000 is blue, everything else is green. So one thing we didn't learn yet, like I said, is break, and it is another new statement. It's a keyword. It literally means to exit the current loop, right? We're breaking out of the statement. We're breaking out of the loop. We can do something repeatedly, 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 and we see break, we stop. It's more often used in the block of an if. If something extraordinary happens, please leave the loop immediately. In this case, if we run out of samples before we run out of pixels, stop. So representing this is a test. We can see this is the output that we have from that. Any visualization of sound is merely an encoding. Right? So we can see a couple different examples of this. Any visualization of any kind is merely an encoding. A line chart, a pie chart, a scatter plot, these are just lines and pixels set to correspond to some mapping of the data. Sometimes data is lost. Recall the mapping of grayscale. Sometimes data is not lost, even if it looks like a dramatic change. Recall creating a negative of an image, then taking the negative of a negative to get back to the normal. Lists can do anything. Going from sound to list is easy. Right? So we have sound to list. We create an empty list. List equals, and then we have two square brackets. We say for s in get samples of sound. list equals list plus, and then we're going to just add the sample to that object, and we return the list at the very end. So as you can see in this example, sound a list return this massive string. If we want to print the zero index of this, we put list of sub index 0. It's 6757. Index of 1, 6852. If we want to print a range from 0 to 100, we can also see that we can do that as well. Can we go from pictures into lists? Of course. We just have to decide on a representation. We'll put a list as an element for each pixel. The number of the numbers in the pixel list will represent the x and y positions, and the green or red, green, and blue component values as well. So picture to list. So here's our example of how we're going to do it, right? We define this function. We say I have a for loop for all the pixels, and then we add to the list another list. So as you can see the double square brackets, that's adding a list inside of a list. And inside that list, we're saying I'm going to have 1, 2, 3, 4, 5 different objects, right? We're going to have X, Y, red, green, blue. Awesome. So then as you can see, here's our doubly nested list, right? Our doubly nested array. It's an array within an array, or a list within a list, whatever you want to call it. So we can see at index or at X and Y locations 1, 1. So that's the first location. We can see that it's 168, 131, 105, 1, 2, 1, 3. 1, 4, 1, 5, and so on and so forth. And that's how we decided that we want to represent our data, because we do have 5 data points per pixel, not as simple as the sound is. And can we go back again and actually make it a picture? Sure. So what we can do is we go back through our list, and then we actually access the index locations because we already know them, right? We know that 0 is the X, 1 is the Y, 2, 3, and 4 is red, green, and blue. We need to make sure that the X and Y fits within our canvas, but other than that, it's a pretty simple code, right? So we can see that there's an if statement that says if P of 0, so if the X is less than or equal to the width, and if P of 1, which is the Y, is less than or equal to the height, then we're going to set the color and we're going to set the pixel. The numbers could have come from anywhere. The numbers in this list came from another picture, but we know that they could have come from anywhere. From multiple sounds, one from each red, green, and blue, from random numbers, from stock market data, from solar radiation. And all we're doing is changing encodings. The basic information isn't changing at all here. What's different is our encoding. The different encodings afford us different capabilities. If we go to numbers, we can use Excel. If we go to lists, we can represent structure more easily. So here's Kurt Gödel, one of Time magazine's 100 greatest thinkers of the 20th century. He proved the incompleteness theorem. By mapping mathematical statements to numbers, he was able to show that there are true statements or numbers that cannot be proven by any mathematical system, or Gödel numbers. In this way, he showed that no system of logic can prove all true statements. Hiding text in a picture. Steganography, we'll go with that, is hiding information in ways that can't be easily detected. One form of it is hiding text information of a picture. Our algorithm for hiding text. We'll draw our message in black pixels on a message picture. We'll hide our message in a picture of the same size. First, make sure that all red values are even. Second, for every pixel where the message picture is black, add 1 to the to the red value at the corresponding x and y. So here's our function to encode the message. So you can go through this example of encoding. Um, One thing to note, I guess we'll step through it real quick. So for the pixels in the get pixel of the original, there's a for loop, right? It goes through and gets all the pixels. If the get red, so if the red value of the pixel, and we have this weird percent sign 2. So if we don't know what that means, this is checking for oddness, right? So the percent sign is the modulus operator or modulo operator, and it actually gives the remainder. right? For example, if I had get rid of pixel, and I say I had was 4, well, 4 mod 2 is 0, right? Because there's no remainder. 2 goes into 4 perfectly. So that's going to fail this first test because it's not odd, right? So if I had any other number, 1, 3, 5, 7, yada yada, and so on and so forth, that mod 2 for sure would be 1 because I know that there's going to be a remainder because it is an odd number. So if that's the case, then I set red to the pixel and I get the red and then I subtract 1 from it. Second, wherever there's black in the message pick, make odd the red in the corresponding image, right? So then I have a double for loop, and you can see that I'm setting the pixels from the message pixel and the original pixel. And then if it's a message pixel, make the red value odd. Definitely go through this. I believe that there will be an assignment that's based on this example. So make sure that you understand this logic and how it works. Um, Go give it a test for sure. You can try something as simple as like in this example where we're meet me at 3 p.m. So in this example, we can see that we're doing the encoding here. We encode the beach with the message, and then decoding is just as simple. It creates a new message picture of the same size. For each pixel, if the red value is odd, make the pixel and the message at the same XY black. Encoding sound into pixel, we can do the same thing, and we can decode it as well. Go back and I'll stay on this for a second so you can try this example as well. And that's all we have for this chapter. I hope that you learned a lot. There wasn't too many examples that we actually could go through. Um, Take the time and go through the encoding and decoding example yourself. It's a little involved, but um, if you step by step and go through it, I think you'll understand it a lot better. It will definitely help you on future assignments where you'll need to know how to encode and decode images and combine them and whatnot. So definitely take those examples. Again, the stuff we mentioned in the beginning with the FTP stuff, not super applicable as far as using it in you're not going to use it as for homework, but it's definitely important to know the protocol. We'll have some discussion posts on that and whatnot. So it's definitely nice that you understand the layers, right? We understand networks, we understand the internet, and all that. But it's also good that we can manipulate pictures and text files and grab websites from different things, and it gives more of a broader use of how we can use JES. So as always, if you have any questions, feel free to reach out. Please take these examples um, and send me an email if you have any questions. Thanks, guys.